And what we have here is we have an equation that we can use to calculate the price elasticity of demand. And so why don't we do that in an example? You can read the example on the slide in front of you. We've got a demand function up here, and we're being asked, oh, it looks like there's a typo. There should be price here. We're trying to find the price elasticity of demand. To solve this problem, we have to find the price elasticity of demand. So we have a formula, and the formula is P over dP multiplied by d prime P. And we want to find maybe the absolute value of this, and it's going to give us the elasticity, the price elasticity of demand. I guess in this case, I'll just use an X for demand. So P is P. We can leave P as P. And we want to replace this term with something that has price in it, with the function itself, so that we can eliminate the prices. And I'm just going to write A price to the power of B, like so. What's the derivative of this thing? Well, we're going to use the power rule. So it's going to be A B price to the power of B minus 1. If we do a little bit of simplifying here, you can see that the A's are going to cancel each other out. And if I normalize the fraction, we get price 1 minus to the power exponent of 1 minus B times B price to the exponent of B minus 1. What is this equal to? Well, this is B price 1 minus B plus B minus 1, which is equal to B, P to the 0. What's that equal to? Well, it's just equal to B. So we end up with the price elasticity of demand is just equal to B. Now the next part of the question is saying, well, suppose B is equal to 3/4, 0.75. How would a 3% decrease in price affect the quantity of demand? All right, so for the second part, we know that the price elasticity of demand is equal to 0.75. If there was an increase in the price of 1%, then demand would fall 0.75%. And if we're going to answer this question using sort of the approximation that we have here, using this first derivative approach of estimating, or well, finding the elasticity at a very specific point, we can multiply the elasticity by 3. So the answer is we're going to decrease the price by 3% and then multiply this by 0.75. Don't need the percentages there. Then we would expect to see an increase in quantity demanded of 2.25%. Up till now, we've talked about price elasticity of demand. But there are other types of elasticities out there. One type is income elasticity. So for example, suppose you got an amazing, nice, large sum of cash through a scholarship. How much more would you end up spending on clothing now that you have this extra amount of money? That would be an example of an income elasticity. We also look at cross-price elasticities. So we might look at the relationship between the cost of airfare and the rates on hotel rooms. We could also look at the elasticity of substitution between inputs. So in 1540, you're going to look at the relationship between labor and capital. You know, how much labor am I willing to give up for 1 unit of capital, such that I can still produce the same amount of output. Those are some other elasticities that we see in economics. And we have kind of a general form. So if we're interested in the, say, price elasticity, then we would have EIP subscript down there. That's the subscript. So this is a price elasticity of what? Price elasticity of demand, the X, the f of X that goes right here. Now remember how to interpret an elasticity. If we have X elasticity of f of X, so for example, before we had the price elasticity of demand, if it was greater than 1, we would say that demand was elastic. The demand was elastic with X, or at X. Here, in the more general sense, we say that f of X is elastic at X. And so if it's elastic, it means that a 1% change in X has a more than 1% change in f of X. In f of X. Similarly, if the elasticity is less than 1, we say that it's inelastic. And that means that a 1% increase in X has less than a 1% increase in f of X. There are some other special cases. If the elasticity is 1, we say it's unit elastic. If it's 0, it's perfectly inelastic. And if it's infinite, then we say it's perfectly elastic. There's also something known as the elasticities as logarithmic derivatives. So let's look at this example that we saw before. Notice that it's actually a logarithm. It's a log linear expression. So if I take the log of both sides here, and I'll take the natural logarithm, we have the natural logarithm of y is equal to the natural logarithm of a plus b natural logarithm of x. And notice that if I take the derivative of the log of y with respect to the log of x, I just end up with b as the elasticity. And we know that's the elasticity because if I don't take the log of this thing, then we end up with the formula x over axb times the derivative of this thing with respect to x, which is a b x b minus 1 which is just equal to b. So we could have taken the log of this thing up here, and then taken this special derivative. Notice that we're taking with respect to log x and log y. So, and it would have gotten us right to the quick answer without having to use the formula that we were using before. Read the question carefully, try it yourself, use what we learned before, pay careful attention. Notice that we have y is equal to log of x, and you want to find the elasticity of y with respect to x, or the x elasticity of y in the terms I used previously. Give it a try. When you're ready, press play, and I'll show you the solution. So the correct answer is B. Notice that I followed the formula. Right? I followed the formula. I subbed in my y expression into the denominator. I solved for y prime by taking the derivative of this thing with respect to x. And I found that the elasticity depends on x. So x is actually showing up in our elasticity formula. The elasticity is going to vary depending on x. Our previous examples did not.